Alright, the other kind of problem that we've been dealing with is stress and stretch distance. Strain and stretch distance. Strain is given by the lowercase Greek letter epsilon is equal to delta over L. If you have a rod and has a length of L and you apply a force to it, then it will stretch out a distance. That extra distance that it stretches from there to there is lowercase delta. So this is a length in inches, this is a length in inches. You divide them and get this unitless number called strain. Typically what they do is they ask you to find out what delta is if you know how much force you're applying to the end of this. And also they tell you what the diameter is. So based on the force and diameter and the kind of material you have, you can tell how much a material is going to stretch. Engineers need to know this. If you're building a bridge, you want to know how much the cables are going to stretch so that you can account for that in, say, a large structure. The equations that connect epsilon and the stress is what's called the Hooke's law equation, where you have sigma, the stress, is equal to the modulus of elasticity times the strain. So this is stress, that's strain, and this is a constant that depends upon the type of material used. Alright, stress, strain, and modulus of elasticity available in table 15.1. So we'll write this down as another given, something you can find in table 15.1 for our particular material. The other equation that will be on the board is our familiar stress equals force per unit area. If you take that and put it in here, and this, and put it over here, you'll come up with an equation that will have only an unknown for that, but we'll have everything else given to you, hopefully. So you put force divided by area, and then that's equal to modulus of elasticity. This is solve and substitute. And then delta over L. What was that, Gerson? What'd you say? What'd you say?
That's good.
Oh, that's good? Okay. You like it? Good deal. Alright, so what was I talking about? Alright, so looking for delta is equal to FL over EA. Pulling this over there and that over there. Flee, basically. Alright, Red Hot Chili Peppers. Okay, so you know what F is, you know what L is. Recall that area is the cross-sectional area. Area is equal to pi d squared over 4. And that would be something that would go right there. So I guess, yeah, there you go. So the diameter would be something that would give you, that would go here. That would help you find the area. Modulus elasticity in table 15.1. Force over there. And I guess they're going to have to give you the length on this to figure out how much it will stretch. So you put this in pounds. This is in inches squared. This is in inches. This is in pounds per square inch. The answer will come out in inches. Okay. So the point, again, find the stretch based on how much force and type of material and length of the material you have. Alright, lastly I have a beam problem. This is a modification of a problem similar to the one we worked in class. Assume that you know that the length of the beam is L. So we'll say that, over here to the side, the given information would be that you're given what L is. And let's just assume that the distance from there over to there, the length of, maybe I should do it differently so it's really clear. The length from right there to right there. Let's assume that that is 3/4 of L. Just make it different than the one we worked in class, something unique. And then we have an angle theta right here, which we could find using tangent or cosine, depending on what, if they gave us this length or the hypotenuse, we could figure it out. But the point behind all of this is to figure out what the tension would be in this cable. Call that T1. Here's force of tension 2. We can already tell that if this is a static situation, that's going to be 100 pounds. If it was moving, it might not be 100 pounds. And because it's stationary, we can say that the force of tension 2 is 100 pounds. Alright, the way to find FT1 for this problem is to make a free body diagram just for the beam. In the problem statement, it should say something about the beam having negligible mass, so that only the weight here would be the overriding force, so that you don't have very many pounds for the beam. That's the usual assumption for these problems in the beginning. We get into advanced engineering, it gets a little more complicated, and you can include the mass or the weight of the beam. Free body diagram should only have forces labeled on it, Ft1, Ft2. The hinge support has a reaction that's upward. It could also be down, but I see that, it's basically trying to support this, so I'm going to assume that it's going to be upward. We're going to call that RY, reaction in the Y direction. This cable is pulling back into the left, so the reaction force on this hinge support is probably to the right, like that. So those are the 4 forces acting on that. That's everything that's touching it, and we're saying neglect the effects of the gravitational pull. I just realized I got something wrong, and that would be that I placed the tension in the wrong spot. I got in the habit of doing it like we did in the previous problem. In the problem we did in class the other day. Ft2 is really right there at a distance of 3/4 L from one end. I want to do a little bit different, that's why I added that. So if you sum the moments about the rotation point O, the rotation point is this hinge support, then the moment due to this one is 0, because moment is equal to RF times the sine of theta. If there is no lever arm, like we see for this one, then we get 0 for that one. Also, this one is going right through the point of rotation, so it also has no lever arm as well. But for the other two, we do have a lever arm. So if we look at Ft1, using the right-hand rule, we see that the R is all the way out to there, so this R turns out to be L. It is a positive rotation, Ft1 times the sine of the theta. Alright, and then the next one is, we have one more term left to go. I always seem to run out of paper here, so we go on to the next one, and the lever arm would be 3/4 L times Ft2 times the sine of the angle between those two. So here's the point of rotation, there's a lever arm, 3/4 L, and there's that. So the angle between them is 90 degrees. So 90 degrees. The reason it's equal to 0 is because we're assuming no rotation. You know what? This one's a minus sign. So this is continued on from there. Should be one long string across there. So minus 3/4 L. So the right-hand rule tells me that this is going to cause, the beam to try to rotate clockwise, which corresponds to minus. Now what you're normally doing here is solving for the tension T1. Should have put a 1 right there. To do that, you move this to the other side of the equation so that you get L sine of theta equals 3/4 L F T2 sine of 90. The L's go away, so Ft1 equals 3 Ft2 sine of 90 degrees divided by 4 sine of theta. This is given in the problem to be 100 pounds. Theta you would find using trigonometry. So normally I would give you this length and that length, or maybe even the hypotenuse, and from those you can figure out what theta is to put right here. Hope this helps. See you soon.